Sorry, I think there are one technical problem. Jim? Jim?
Yes, do you hear me?
Yes?
I think it was canceled due to some kind of agreement
Yes, yes.
that yes.
Can you start over, please?
All right. Should I start
Yeah, from the beginning, please.
from the
Sorry.
beginning?
Yeah.
Okay. Okay. All right. Hello, everyone. Today I'd like to introduce the Condela Challenge for our Qiskit Fall Fest hackathon. And this is a special collaboration bringing together three incredible organizations. First, we have Mela, a deep learning research institute based in Montreal, Canada, doing cutting-edge work at the intersection of quantum computing and AI. Then there's AMF, Quebec's Financial Markets Authority, for exploring quantum computing applications for financial forecasting. And finally, we have Condela, a photonics quantum computing platform. Together, we have this exciting prompt called option pricing in finance. And I think this is going to be an exciting journey into the world where the quantum computing meets finance. So, what's this all about? Well, the main goal of this prompt is to calculate the price of options using quantum computers. This hackathon is structured into two distinct tracks, so you can choose the one that interests you most. Now, track 1 here focuses on quantum random walks for pricing put and call options. Track 2 is all about swaptions pricing using quantum machine learning. Both tracks are exciting in their own way, and I'm gonna walk you through each of them in detail. So let's start by diving to track 1. In track 1, your goal as a participant is to calculate the price of put or call options using a quantum random walk. So we're going to use the Black-Scholes model as our foundation here. This is a well-known model in finance that has a simple analytical formula, which means you'll be able to benchmark your quantum results against exact solutions. This model assumes constant interest rate and volatility, which makes it a great starting point for exploring quantum approaches. Now, I want to be clear about expectations. The option prices you calculate can be approximate, and that's perfectly fine. We are not necessarily looking for exact price calculations, but rather a method that can effectively approximate the price of options. We're exploring quantum methods here, so approximations are part of the learning process. And I know this might sound challenging, but this is absolutely achievable within the hackathon timeframe. And you'll have all the resources you need, and we've designed this. I think it is designed to be approachable even if you're still learning the Qiskit. Here you can see a visualization of a classical random walk, also called Brownian motion. This is a fundamental concept that underpins how we model stock price movements. The Black-Scholes model is actually based on this classical random walk assumption for asset returns. In classical finance, we use random walks to simulate how prices might move over time. And in this track, we're taking that concept and implementing it using quantum circuits. So instead of simulating all paths one by one, like in a classical random walk, we'll use a quantum walk to discretize the Black-Scholes equation. And this technique offers a potentially much faster way to explore all possible future stock price scenarios simultaneously. To give you some real-world context, here's a chart showing S&P 500 returns over time. The S&P 500 is a well-known market index in the United States. And you can see how stock prices fluctuate and sometimes like dramatically. This historical data gives us a sense of volatility and randomness inherent in financial markets. And in these financial markets, many participants buy and sell put and call options on indices like the S&P 500. And a lot of financial institutions actively trade these kinds of options. So if you're curious to explore more data like this, you can check out the Macro Trends website here for comprehensive historical chart data. Now, let me quickly explain what put and call options actually are, and in case some of you are new to finance. A call option gives you the right to buy an asset at a specific price at a specific point in time. A put option gives you the right to sell an asset at a specific price and at a specific point in time. That specific price we are talking about is called a strike price. For example, imagine you enter into a call option contract to buy one share of the S&P 500 at $10,000 in 3 months. The $10,000 would be the strike price. The assets would be the S&P 500, and the maturity would be 3 months. You're essentially betting that the stock price will go above the strike price, making your option valuable. Now you can have options with different maturities, 3 months, 9 months, and 12 months, and so on. In the financial markets, there are even more complicated options being created at all the time. But for this track, we are focusing on these well-known and simpler call and put options. So, what are we giving you to work with track 1? First, we'll provide you with the analytical formula to calculate put and call options using the Black-Scholes model. We'll also give you code for a classical computer that calculates the exact price of these options. This classical implementation serves as your baseline, and you'll be able to directly compare how well your quantum approach approximates the analytical solution. This will be your benchmark, your reference point for evaluating your quantum algorithm. And of course, we'll provide all the parameters you need to calculate option prices. Things like strike price, asset price, interest rate, volatility, time to maturity, and like so on. You have everything you need to get started, right? So, and here's what we are asking you to do. Your goal is basically to obtain an approximate price for put and call options using a quantum random walk. You'll be working with the parameters we provide, and you'll be building your quantum circuit to solve this problem. The one thing to note, we will not be providing a data set of option prices for track 1. Instead, you'll be working directly with the model parameters and approximating the analytical solution. If you want to dive deeper into the theory, I highly recommend checking out the paper by Han and Song from 2025. It's called Quantum Walk Option Pricing Model Based on Binary Tree, published in Physica A. And this paper explains an algorithm for how quantum random walks can be used to price options, and it will give you excellent background on the approach. Now let's move on to track 2. This is where we bring in quantum machine learning for options pricing. Before we dive into the details, let me give you some context about where quantum machine learning fits into finance today. So we are seeing applications in portfolio and credit risk using combinatorial optimization techniques like VQE and QAOA. And there's also interesting work happening with quantum kernels and QSVMs for small structured datasets in market modeling. For time series forecasting, quantum reservoir computing and variational circuits are showing promise. And this is exactly what we'll be focusing on in track 2, treating swaption pricing as a time series prediction problem. Now I want to give you a reality check here. Near term often matches or sometimes even trails strong classical baselines. We're still in the early stages of quantum advantage in finance, but that's what makes this exploration so exciting. And you'll find several great references here on the slide for further reading if you want to explore more about it. Now, to understand the swaptions, we first need to understand interest rate swaps. An interest rate swap is a contract between two parties. One party agreed to pay a fixed interest rate, while the other pays a floating interest rate. In other words, they exchange payment obligations. So you can basically think of it like this. Company A and Company B enter into an agreement. And Company A might want the stability of a fixed rate, while Company B is willing to take on the risk of a floating rate. So there's a flow of fixed interest rate payments from Company A to Company B, and Company B pays floating interest rate payments back to Company A. They essentially swap their payment obligations. Now, a swaption is an option on this interest rate swap. When you buy a swaption, you're paying a you're paying a premium for the right, but not the obligation to enter into this swap agreement at the later date. It's essentially an option that gives you flexibility on whether to execute the swap. So what will you be working with in track 2? We are going to provide you with a synthetic dataset of swaption prices. This synthetic dataset was generated using a realistic model that was calibrated on actual market data. So while it's synthetic, it accurately reflects real-world pricing patterns and market conditions. Essentially, this is a time series forecasting task where you'll need to handle both missing data imputation and future price prediction. Your goal is to use quantum machine learning models to accomplish 2 things. So goal number 1, predict the values of missing data in the dataset, because real financial data can be very noisy and incomplete. And goal number 2 here, predict future options prices for the next 2 weeks. This is a classic forecasting and imputation problem, but you'll be tackling it with the quantum tools. Now let me show you what this dataset looks like. Swaptions have 2 key parameters, which is tenor and maturity. Maturity is the moment at which an option can be exercised. And tenor is the length of time or the duration of the interest rate swap payments. In this table down here, you can see we have different combinations of tenors and maturities. So for example, you might have a tenor of 10 years and a maturity of 30 years. or a tenor of 15 years with a maturity of 30 years. And you'll notice here some entries are marked as missing data. And you'll also see entries marked as like future data that you'll need to predict. So your model needs to learn the patterns in this time series data and fill in those gaps. The actual data sets you'll be provided with is much bigger than what you see here. And so this is just a small screenshot to give you an idea of the structure. For track 2, you can use various quantum machine learning techniques. Quantum reservoir computing is one option, but feel free to explore other techniques as well. Your goal is to train a quantum machine learning model that can predict missing values and forecast future option prices. And this is where creativity and innovation really comes into the play. And now here's a practical baseline approach for the quantum reservoir computing method. This is just one way to approach the problem to give you a starting point. So start by encoding an input window. Let's say the past 20 trading days of features into your quantum reservoir. This reservoir acts as a feature extractor that you want to train. It's a fixed quantum circuit. Then collect the reservoir states, which might be photon count histograms or mode quadratures if you're using photonics. If you're using gate-based quantum computing, these should be measurements and qubit expectation values. These quantum measurements can be seen as quantum features. Train a linear readout using reach or lasso regression to impute gaps and predict prices over a 1 to 10-day horizon. Use walk-forward cross-validation and compare your results to classical methods like gradient-boosted trees and small LSTMs. This will help you establish baselines and see where your quantum approach stands. And finally, report on accuracy and memory capacity versus your reservoir parameters. Things like circuit depth, non-linearity, and noise tolerance. So this will help you understand what's working and where quantum methods might have an advantage. Now, let me summarize what materials we are providing for both tracks. So for track 1, the quantum random walk track, you get videos and documentation covering finance background. We'll explain puts calls volatility and the Black-Scholes model in detail. You'll receive the data, which includes the parameters of the Black-Scholes model, things like asset price, strike price, volatility, interest rate, and maturity. And we'll give you additional resources, including a function to compute option prices with the Black-Scholes formula as your reference. This gives you the exact mathematical model, so you can basically benchmark your quantum results. Now for track 2, the quantum machine learning track, you get videos, also the documentation, assumptions, and the financial background you need. And most importantly, you'll receive the data as a CSV file with the complete data set of option prices. This includes data points at different time steps with various tensors and maturities. So you'll have everything you need to train and test your quantum machine learning models. Okay, so please, before we wrap up, please don't hesitate to ask questions on the Conda Challenge channel. And also, I'd like to invite you to discover the website for this event we have here. You can find all the details. And both tracks offer concrete use cases where quantum computing meets the real financial problems. Okay, so Thank you all for your attention and good luck with your projects. Thank you very much.
Thank you, James, for this very nice introduction about Quantela challenges. Right now, we're moving forward, moving on the Anthropica Labs challenge. Please, Leo, share the screen.
Yes, hello everyone. Can you hear me?
Yes, very well.
Fantastic. So I will be very quick. So I hope you can see the screen.
Yes.
Great. So everything in one page. It's going to be pretty simple. Definitely not there yet with such a sophisticated hackathon like the one we just witnessed with the Quandela folks. So for this challenge, what we thought is try to bring your own code to Loom Design. As I mentioned the other day, Loom Design is a brand new piece of software. There's tons of work that can be done. And we believe one of its most interesting feature is that of being able to accommodate any stabilizer code. So the challenge would be, as you can read here, there is a bunch of small codes, the 832 or the 1644. These are both color codes. You can check them out on the error correction zoo, and your task would be to implement them within Loom. Now, there are several ways in which you can do this. If you look in the Loom documentation, you'll see a tutorial for a different color code that can serve as inspiration, or you can look at the way we've built within the source code, for example, the Steam code or the repetition code if you want something more complex, or the 5-qubit perfect code. And you can choose how to tackle the problem. If for any reason you don't like those two codes, feel free to look up another one from the zoo, and you can also try to implement it. So we do give some freedom. The idea here to evaluate your answers will be maybe slightly less subjective, but it will be in terms of, is the code working? And how well have you sort of designed the code? Is it doing things as it's supposed to do? There's a lot of bits and pieces of Loom you'll need to learn in order to complete this challenge. And our GitHub place is the best place where you can get some help, and we will try to support you throughout. Let me also stress, Loom is a pretty new piece of code, so you may find some rough edges here and there, which is always a little bit unfortunate. The upside is that being a new project, in a sense, and in the open source sphere, you really get a chance to contribute early and to make some impactful contributions to the code base. So that's all on our end. Thank you so much for your attention, and I hope you will have fun adding these codes to Loom.
Thank you for this very nice introduction about Anthropica Lab Challenge. Right now, we're moving forward to yes, Antoine. Yeah, he will present about Agora platform, about how you will submit your projects. Please come.
Yes, should I connect my computer?
You can join the Zoom link.
Where is it? Is it?
Yeah.
Thank you. Ouais, je me suis connecté. Sinon, je peux le faire sur l'ordinateur. Je pense que ça sert à rien. Does everyone see my screen now?
No, we can't. Can you open the all?
The what?
Yeah.
I'm sharing now. Oh, it's not working.
I think no. Stop. That is it.
I'll try this. Oh, and this. Still not working.
No, still not open.
Yeah, sorry about that. I'll leave and rejoin with maybe.
Yes.
Oh, yes.
Now open.
Good. Okay.
Yes.
So this will be surely your main point of entry. The Qiskit Fall Fest event. But first, let me introduce Akora. We're a company providing some use cases. Well, rather, really use cases providers. But this is where you can find competitions to participate in offline and online hackathons. We have many events currently happening, but also all kinds of competitions, which I will present briefly, on top of all the previous participants that spoke. But you can see also that we have a discussion space and dataset space where you can download and upload your own datasets. For example, here we have the AMLib binary optimization, and you can also cite these datasets here, and you can also copy directly the byte text so that you can quote it in your paper. Anyway, this is Akora. We also have a blog where you can find exciting articles. And back to Qiskit's Fall Fest event now. So yeah, this is the event page for all the challenges. So here you can find Condela's challenges. You can find Anthropica Labs challenge. And there is also a tutorial included so that you can maybe spend some time on our tutorial. Maybe right now, maybe later, but yeah, feel free to participate in that one. So yeah, this will be your main entry point. We have a discussion forum here where you can find some information about the event in general. I recommend that you subscribe here if it's not already the case. And after that, you can navigate into the competitions and find the description of the competition. And after that, you can you do your own thing. And then after that, once you are ready to submit, be sure that you check the rules here and accept the rules. And then after that, you can go in the submission. Yes, that's because I'm not a member yet. I'm gonna add myself. And after you've accepted the rules, you can drag and drop files of your choosing inside here so that they can be reviewed by the jury by the jury team that will be selected sometime. Right now it's Pierre Augustin for now. Maybe this will change. I think this will change. The jury members.
I do remember, yeah.
They will soon be selected, right? Yeah. And there is also scoring criteria that the jury members will have to follow. And then after that, you will find your score in the leaderboard here. And yeah, the score, the higher the score, the best, you will be ranked first for the higher score you make. And if there are equal scores, the first person or team that's submitted will get placed first. And this is where you will be able to find your score and the score of others. I guess there will be some badges that will be awarded at the end of the hackathon. So this is a great way to create your Aqua profile, and so that maybe in the future you can quote that also in your curriculum. Well, no, sorry, in your resume. And to finish, there is also the discussion forum for the competition itself. So if you have questions, please post in the forum of the competition itself instead of the event in general. If you have questions about the event in general, please post your topic there. And if you do not have a team yet, but you want to find a team, you can go inside the team settings tab, yes, just like that. And you can flip the switch here so that you find people that are looking to recruit in their team or that want to join a team in general. And this is to select your team here. I myself have multiple, but here I can join with my own, or I can create a new one here, which should be fairly easy. Should give a name to your team, a username, which is globally unique on Akora, and a profile picture if you choose so. You can also create more, but this is the bare minimum right here, the first two fields. And yeah, that will be all for me. If there is any question, please reach out in the discussion forum, but I can also leave my email address in the Microsoft Team channel so that you can reach out if you have any problem. I think the competitions are public right now, so you should be able to see them all. Check that. Oh no, it's invited members only. So if you join the event, you should have access automatically to the challenge. But yeah, feel free to reach out by email. Send it right now in the chat. And yeah, this will be all for me. Is there any questions in the room?
Yes, I have one question.
Yeah.
So when you click on the event, for example, here, this, and do we have to click on a join event on the right to participate on a?
Yes, yes. Or else you will not be able to see the competitions. The event in itself can be freely joined and everyone can see it, but you have to click on join event to see all the challenges. Or apart from the tutorial here, which is visible to everyone.
Yes, thank you. Thank you. So if there are any questions, please reach out Antoine, or you can post on discussion, right?
Yeah.
Put the question on discussion, and then Antoine and our team will try to answer it. So I'm moving on. The last detail about the hackathon. Sorry. So okay, so just a little bit about the timeline. The hackathon is officially started today on 21st, and then you will have 1 week to form a team and then work on the projects, choose the projects, and you can also choose multiple challenges if you want. And then 1 week later, we hope that on 21st November you can submit your work, and the 5th December we will announce the results. So right now, the question is, what do you have to submit? In this slide, I just want to quickly summarize what we have to submit. First one, we need your GitHub repository. It should be submitted on a website, and also instead of organize a meeting for your presentation, we would love you to record a video presentation. It lasts 5 to up to 7 minutes, and also it should be uploaded on a website. And one thing you have to make sure that you have to acknowledge our sponsors on your presentation slides. And to finish, I will announce the prize for the winners. We would like to divide it by 2 tier prizes. The first one, for the technical prizes, we would like to give for the first and the second place of the hackathon around 500 euros for the first place, and the second one is 200 euros for the second place. And also we will have an additional prize for the team who would like to share their presentation on the social network, and we will give a little prize for the team who has the highest views on the social network, social media. So that's all. And I would like to thank for all our sponsors for helping us to make this hackathon happen. And also I would like to thank for all the participants for the hackathon, and good luck for all of you. Thank you.